All right, so continuing on, what I was saying is that the carbon-oxygen bond, its stereochemistry doesn't change when we exchange the hydrogen for a tosylate. Okay, so when you just put the tosylate on there, that doesn't change the stereochemistry whatsoever. But now what you've done is you've taken a poor leaving group. So remember that a hydroxyl group is a poor leaving group. So poor leaving group, and you've converted it into a dandy. So this is a good leaving group. All right, so now we have a strategy to make our own leaving group, which is pretty cool. We can just take an alcohol and convert it into a tosylate, and you make a good leaving group. There you go. So now, once you've got the tosylate on there, you can treat it just like you would an alkyl iodide, bromide, or chloride. Same thing. So if you were to take your tosylate, if it's a primary tosylate, treat it with a strong base, strong nucleophile, you're going to get mostly SN2, a little bit of E1. If you had a secondary, and then it flips, you get mostly E2 with a little bit of SN1. Give me a thumbs up if you're with me on that. A tosylate is going to act this exact same way as an iodide would. Awesome. Awesome. There you go. So, a good organic chemist has to have all kinds of tricks up their sleeve, so to speak. So let's see if we can try some problems here. So the first one, we'll start with A. We've got a good leaving group. So this is a secondary tosylate. Tosylate. We've got a strong base. Strong base. And it's also a strong nucleophile, ethoxide. So could anybody tell me what pathway is going to predominate here? What would be the major product or major pathway? Would it be SN2 or E2? If you have to go back and look at the table, do it. Anybody can tell me what the major pathway? We're going to get both, but which one's the major? Yeah, it's the E2 pathway. So the E2 is going to predominate. And so there's only one type of beta proton here. So we get the E2 product as the major product, right? And then we're going to get some SN2 as the minor product. So we'll put here that we're also going to get some SN2. And so this would be the minor product, minor product. So again, this is from SN2, and this one here is from E2. All right, let's try the next one. So the next one, we have a secondary tosylate. So pencil structure in here, OTS, okay? And we're treating it with sodium hydroxide. Well, hydroxide, I'm just going to write out the anion, right? Hydroxide is a strong base, but it's also a strong nucleophile. And I have a secondary tosylate. So what's going to predominate here? What's going to predominate? Would it be elimination or substitution? Anybody? What would predominate here? Would it be elimination or substitution? It's secondary, and we have a strong base, strong nucleophile. It's the exact same scenario that it was in A. Exactly. The E2 reaction is going to predominate. So if we look at the molecule, you can see if this is our alpha carbon, we have beta protons here, and then we also have beta protons here. So you could pull off either one of those, right, to do your E2 reaction. You're also going to get some SN2 in this case. And so for the E2, right, the base is going to rip off the proton. We form the double bond and we lose the leaving group. And that would give us what? It would give us this as our product. So we end up with this one, something like this. If you were to pull off the proton in blue, then you would end up with this compound. And if you were to do the SN2, you would just do a substitution of the tosylate with the hydroxide. And of course, you would invert the stereocenter like this. So there you go. This product comes from SN2. And both of these products up here come from E2. But there's one product I'm missing. Can anybody tell me what it might be? There's something that's missing here. There's one more E2 product that I haven't drawn. So keep in mind that these two compounds here, these are regioisomers, exactly. regioisomers. But there's another stereoisomer of the blue compound, isn't there, Katana? Right, this compound is trans, and so I also have to include the cis. Right, 1, 2, 3. So I can pretty that up. 1, 2, 3, 4, 5, 6. There we go. So this is going to be the cis, and this is the trans. So I get two stereoisomers here. So I get a total of 4 products in this case. I get the E and the Z, or the cis and the trans, of the most substituted alkene. And then I get the Hoffman product in red, and then I get the SN2 product in black. Now, between the cis and the trans product, which one of these do you think is going to be the major product? You look at these two, which one is less sterically hindered? Would it be the cis or the trans? It's going to be the trans, exactly. So this will be my major product. And there you go. Now we've identified all 4 of the products that you could form in this reaction. So let's continue on with this chapter by talking about alcohols just for a second here. There's a couple of kind of things that I have to remind you of, or kind of go over with respect to alcohols here. So it says here, alcohols can also be used in substitution and elimination reactions and used as starting materials to make alkyl halides and alkenes. So here we're taking a primary alcohol, okay, and we're treating it with HBr, and we're making it a primary alkyl bromide. Now, why would this work? Right, because we know that hydroxide is a poor leaving group, right? It's the conjugate base of water, which is not a strong acid. And so why would this work? The reason why it works is because HBr is a strong acid, and so it can protonate the alcohol to convert it into an oxonium, and now this is going to be a good leaving group, okay? And then once you've converted it into a good leaving group with the hydrogen ion, with the proton, you've got bromide left over, which can come in, and we get our nucleophilic attack and our loss of leaving group, and there you go. It occurs via an SN2 mechanism. So you need to know that you can take a primary alcohol, treat it with HBr, and make a primary alkyl bromide. So it says here, if you have a tertiary alcohol, well, how is that going to react? In that case, it can react via an SN1. Okay, why would it react via an SN1? Because you can take the poor leaving group, convert it into a good leaving group, all right, which is going to leave and form a stable carbocation, and then the bromide can come in and do a nucleophilic attack, and of course it can attack from either face of the molecule here. So it's just the mechanism. So I'm reading from the top here. The mechanism is either SN1 or SN2, depending on the substrate. Primary alcohols react by SN2, but secondary and tertiary, they're going to react by SN1. So a primary is via SN2, but a secondary and tertiary is going to be via SN1. All right, so you want to keep that in mind. So strongly acidic conditions are also considered to be protic conditions, which would favor SN1s, but since a primary carbocation is too unstable to form, a primary alcohol is not going to react by an SN1, it will react by an SN2. So I got one more reaction to show you before we get into the end of the chapter. And this is one of my favorite reactions of all of organic chemistry. Why? Because it's simple. And I like things, the easier it is, the better it is, right? And so it says here, an alcohol will undergo an elimination if you just heat it up with sulfuric acid. Now think about it. If you heat up yourself, what do you lose, right? If you go outside and do some strenuous exercise, you're going to lose some water. And so when we heat an organic molecule up enough, we can lose water from an alcohol. And so this is one of the cheapest, simplest reactions you can do. If you take an alcohol and heat it up in acid, it loses water, it makes an alkene, and it usually gives you the most stable alkene you can get. And the mechanism is exactly what you think it would be. It's just a proton transfer to take a poor leaving group and convert it into a good leaving group. Then once you have the good leaving group, it's going to leave in this case because you have a tertiary substrate. And then you could do a proton transfer to produce the alkene, and that's it. Again, this is one of my favorite reactions in organic chemistry. I mean, think about how easy this thing is to set up. You just take your starting material, put some sulfuric acid, and heat it up. I mean, it doesn't get any easier than that in organic chemistry. Now, if you're like, could we practice this mechanism or this type of mechanism? Absolutely. Let's take a look at this problem here. It says draw a plausible mechanism for the following transformation. So we have a tertiary alcohol be converted into a tertiary alkyl halide. So is this going to occur via an SN2 or an SN1 mechanism with HBr, based on what we saw in the previous slides? It's going to be an SN1, isn't it, right? Because you have a tertiary alcohol. So let's draw the mechanism. So we're going to start with our alcohol. I'm going to redraw it like this. Always a good idea to redraw everything. So we're going to do a proton transfer from our HBr. So we're going to grab that proton, and then we're going to convert an alcohol, which is a poor leaving group, into an oxonium, which is a dandy leaving group. So I'll just write this here. All right. And now our leaving group is just going to leave. Why? Because we end up with a tertiary carbocation. So we end up with a tertiary carbocation like this. I'll ask you guys, is this tertiary carbocation going to rearrange? And it's not a trick. This is not designed to fool you. Is this going to rearrange? No, not at all. And so in the very last step, the bromide is going to come in as a nucleophile. And we get a nucleophilic attack. And there's no stereocenter in this molecule, so we don't have to worry about that. And that gives us final product. And there you go. Hot dog, we have a wiener. It is done. It is finished. There you go. Pretty straightforward mechanism. And again, this is a mechanism I would expect you to be able to draw. This mechanism here. Well, that brings us to another mechanism here, 7.34. So now we're going to take this alcohol and we want to convert it into this alkene. And so this is going to be an E1 reaction, right? And that's based off what we just saw in the previous slides. So what's the first step going to be here in the mechanism? Could anybody help me out with the first step? Is it going to be a nucleophilic attack, loss of leaving group? What would be the first step if you're taking an alcohol and treating it with strong acid? Going to be a proton transfer, exactly. Now, what's going to be our acid? Remember, you're going to have an equilibrium between sulfuric acid. Sulfuric acid is dissolved in what? It's not a trick. What is sulfuric acid dissolved in? Water, exactly. So you've got H2SO4 in water, which is in equilibrium with hydronium and HSO4 minus. So which one of these is a weaker acid? H2SO. That's weird. Anyhow, come on. There we go. H2SO4 has a pK that's equal to -9. Hydronium has a pK that's equal to -1.7. And so the equilibrium is going to lie to the side of hydronium. Son of a gun, what am I doing here? There we go. It's going to lie to the side of hydronium. So the major acid present in solution is going to be hydronium. So we're going to draw a hydronium ion like this, and we're going to do a proton transfer in the first step. So we're going to convert that good leaving group, or that crappy leaving group, I should say, into a good leaving group. So let's do this. There we go, and we get OH2. Right, like that. And then my leaving group is going to leave. So we're going to get the leaving group leaving because it's secondary. It can do that. And we end up with a secondary carbocation, which looks like this. Is this going to undergo a rearrangement? Oh, you bet your Bobby socks it will, right? Because this is secondary, right? And if we do a methyl shift, we end up with a tertiary carbocation. So we end up with a tertiary carbocation like this. All right. And then to get to the very end, to get from here to here, we have water, which can come in and behave as a base. And it's going to pull off this proton here. So we end up yanking off that proton and we form the double bond. And that is it. Again, this is my favorite reaction. reaction where you just heat the snot out of something, pardon my language, and you end up with an alkene. Again, very straightforward reaction. All you have to do is heat it really hard. All right, in sulfuric acid, which is super cheap, at least I guess comparatively speaking. All right, so that brings us to the very last section, which is just kind of a review of everything that we've covered so far. So take a look at this. So take a deep breath here and just realize, okay, this chapter has a lot of information. What's the point of all this stuff? What's the point? It says the whole point of organic synthesis is to make valuable complex compounds from cheap and readily available starting materials. So I worked as a medicinal chemist most of my life, most of my adult life. And so, what I was always trying to do is make a new molecule that could be used as a medicine. And so a lot of times these are things that were very complicated and very expensive to make. So we took cheap starting materials that we could buy from a supplier usually, and then we would do synthesis, or we would design some kind of synthesis to make the molecule that we wanted. And it says, you know how to make a variety of compounds starting with an alkyl halide. Now let's think about each one of these, okay? If you took a primary alkyl halide and treat it with hydroxide, that's going to do an SN2 to give you an alcohol. Okay, well, that's good. What if I took my alcohol and treated it with HBr? Well, I know that that's going to do an SN2 after protonation, right? That will do an SN2 to take me back to the primary alkyl halide. So I can go back and forth. Here's another reaction we just looked at. We said, okay, well, if you have an alcohol, you can turn it into a tosylate. And if you have a tosylate, well, that's a good leaving group. So if you treat it with a strong nucleophile, right, a primary tosylate, that's going to make the alcohol. We also said that potassium T-butoxide is a hindered base, right? Hindered base. And so if you treat a hindered base with a primary alkyl halide, that's going to give you an E2 reaction to make an alkene. We also said that you could have other hindered bases with a primary alkyl halide instead of an alkyl tosylate. You could use DBU, DBN, T-butoxide. These are all hindered. So hindered bases. All right, we said you could use an alkoxide, right? Methoxide is a nucleophile. That will do an SN2, right? And make an ether. So now you've learned how to make an ether. You could take hydrosulfide, which is the SH minus ion, and now you can make a thiol, right? And that's another SN2 reaction. This is one that we haven't looked at in detail, but this here is called an acetate. So this is CH3CO2, and you get a negative charge here. So this can do an SN2, right? Nucleophilic attack, loss of leaving group. And if you do that, you end up with an ester. So now you've learned a way to make an ester. So this again is called an acetate ion. And this is an SN2. And of course, a nitrile, if you take cyanide, right? Cyanide is a good nucleophile, right? It could do a nucleophilic attack, loss of leaving group, and that will make a nitrile. So now you've learned how to make all kinds of crazy functional groups: a nitrile, an ester, thiol, ether. What else? An alkene, tosylates, alcohol. So that's with primary. What about tertiary? Right, we've learned a bunch of different things we can do with tertiary alkyl halides. For example, you can do a solvolysis. This is kind of where we started the day. This was kind of our Thursday morning, beginning. We said you could do solvolysis. So that's what this is called. This is solvolysis, okay? Then we said you could take the tertiary alcohol, treat it with HBr, and that would make a tertiary alkyl halide, right? That's an SN1 reaction. All right, then we said you could take the tertiary alcohol, convert it into a tosylate. Tosylate's a good leaving group, the same way a bromide is. So if you treat this, or this with sodium hydroxide, either way, you're going to get the Zaitsev product is the major product, and you're also going to get some of the Hoffman product too. Then if you switch the base to a hindered base, well, in that case, the Hoffman's going to be major and the Zaitsev would be minor. And then I told you my favorite reaction is this one right here, where you just take an alcohol and heat it up really hard with concentrated sulfuric acid. You can put heat in here if you want. And that gives you the Zaitsev alkene is the major alkene. So we've learned a lot of different reactions in here. And so, you can do this whole brick house analogy if you want. You've got to have plans. You want to draw the house before you start building it. But there's something that I'm going to bring up quite a bit in this class, And it says here, organic synthesis is like this. We look at the product first, and then we decide what would you need to make that product. And we call that retrosynthesis or retrosynthetic analysis. Sometimes I'll just say retrosynthesis. And retrosynthesis comes in really handy. Basically, if you're like, I don't understand what retrosynthesis is we kind of solve the problem backwards sometimes. We'll look at a product and say, what's the only way I could make this molecule? Right? Like an example would be this molecule. Let's say I asked you to make this molecule, this ether. What's the only way you know how to make an ether? Well, I just showed you with an SN2 that if you started out with this, so 1, 2, 3, 4, 5. If you started it with this alkyl halide and you used sodium ethoxide, so remember ethoxide is this would do an SN2 on that, and that would give you the desired product. 1, 2, 3, oops, let me change the colors here. My blue. 1, 2, 3, 4 carbons. No, 1, 2, 3, 4, 5 carbons, sorry. And that, all right, give me a thumbs up if you follow me on that synthesis. The one I have written on the top. Just an SN2 between an alkoxide and a primary alkyl halide. Okay, yeah, cool. So that's just an SN2. And if you're wondering, could you make it the other way, Mr. Dion? Could you make it like this? Could you take this alkyl halide and treat it with 1, 2, 3, 4, 5? Could you use this alkoxide? Sure, you could do that too, right? That will give you an SN2, and that's going to give you the product. But the bottom line is that we looked at the product and said, well, what's the only way we know how to make that? And that's something we do a lot in this class. So I'm not going to go over all these because it's just the same old thing. And they said since the mechanism is SN2, they chose DMSO as the solvent because it's polar and it's aprotic. So there we go. And again, I'll talk about more about solvents later on, so don't stress about it right now. And so, like, let's say you wanted to make this molecule here. There's an ester. So you've got the acetate. So you'd say, well, retrosynthetically, and this is a retrosynthesis arrow, retrosynthesis arrow. It's 2 lines going backwards and then a little point on it. Well, you'd say, well, if I had the acetate, right, which we just looked at a few minutes ago, and I treated that with a primary alkyl iodide like that, that would do an SN2, nucleophilic attack, loss of leaving group like that. So again, even if you're not following me 100%, you're going to have to practice this on your own. But the idea is that you say, okay, well, what's the only way I know how to make this functional group, right? What's the only way I know how to make an alkene? Elimination. So it's got to be some kind of elimination mechanism. I'm not going to get into the details of who invented retrosynthesis, but I'll just say it helped to make them even more famous than they already were. All right. So we've got some really interesting problems here. It says for each of the cases below, transform the given starting material into the target molecule. More than one step might be required in order to plan a reasonable synthesis. It might be a good idea to start with a retrosynthesis. So let's see if we can solve these problems and figure out what the reagents are that we would need here. Let's see if we can figure out the reagent. All right, so for the first one, if this is my alpha carbon, right, we know this is some kind of elimination reaction, right? We have a secondary alkyl halide, so it's probably an E2 reaction. If this is secondary. Now, if this is my alpha carbon, that means that I have beta protons here, and I also have beta protons here. Now, I want to rip off the beta proton in blue. If I want to pull off the beta proton in blue, am I going to use a hindered base or an unhindered base? If I want to pull off the proton in blue, would I use a hindered base or an unhindered base? I want to preferentially pull off the proton in blue. Because if I pull off the proton in blue, I'm going to get this product. If I pulled off the proton in green, then I would get the Zaitsev product. So would I use a hindered base or an unhindered base? So in this case, I'm going to need a hindered base, right? Because if, remember, this product here is more stable right? Because it's more substituted. So you want the less stable product. You want the Hoffman product, right? This is the Hoffman product. So how am I going to pluck this guy off, right? If I have a hindered base, or sorry, an unhindered base, it's going to pluck off this proton to give me the most stable alkene. But if I have a big old bulky base, like a T-butoxide, for example, it's so big and bulky that it can't get in between these two methyl groups to grab this guy. It has to go and pluck this proton, which is kind of on the periphery, if you will. Does that make sense to everybody? I hope so. All right, so let me just delete some of this stuff here. So what's going to happen is if you draw the molecule out, draw this here, and we put in the proton in blue, okay, a big old hindered base like T-butoxide is going to pull off this proton, make the double bond here, and then we're going to lose the leaving group like this. So the answer is you would use T-butoxide, so potassium T-butoxide, and we abbreviate it like this. All right. For the second one, we want to pull off the proton in green, right? We want to pull off this proton to make the Zaitsev product. So for that, would I use a hindered base or an unhindered base? Because I needed to squeeze in between those two methyl groups. I need an unhindered base. So give me an example of an unhindered base I could use. What's an unhindered base I could use? Yeah, exactly. Like Sean said, I could use sodium hydroxide, or I could use methoxide, or I could use ethoxide. They will all work. Any one of those is an unhindered base. So these are all are unhindered. All right, and for the last one, we want to make the more substituted alkene from an alcohol. So for this one, we can just heat it up in sulfuric acid, and that will do the trick. That's one way of doing it, but there is a second way of doing it. You could also take the alcohol and convert it into a tosylate. So to do that, it's a two-step process. It's a one-step process. We use tosyl chloride and pyridine, and that would make the tosylate. So now we've got a good leaving group. We've got two types of beta protons. We have the one in red, and then we have the one in blue. If I want to pull off the one in red, would I use a hindered base or an unhindered base? Exactly. I'd use an unhindered base, like sodium methoxide. So I'll just put in here NaOET, and that will give me the product. So I'll just write product here. Either way is going to work. All right, I just want to show you a little bit more about this whole solvent thing, about polar product solvents and polar aprotic solvents, and then we're officially done. So going back to polar product solvents, I told you that polar product solvents were polar. So we'll put here polar product solvents. Are polar is number one. And by protic, it means they are capable of doing hydrogen bonding. Hydrogen bonding. And so you can see in each one of them, they all have the capability of hydrogen bonding: ammonia, acetic acid, ethanol, methanol, and water. So these are going to be the preferred solvents for SN1 and E1 reactions. And then if we go to polar aprotic solvents, so of course they're polar, right? They're polar. Yes, but aprotic means no hydrogen bonding in the solvent. Okay, so these are going to be preferred for SN2 and E2 reactions. And some examples are DMSO. You saw that in the notes earlier. That's dimethyl sulfoxide. Acetonitrile is this guy here. You saw DMF earlier on. That stands for dimethyl formamide. Acetone and HMPA is another. So those are solvents that we see for SN1 and SN2 reactions. And I'm not going to go into the solvent effects in detail. I mentioned this briefly earlier on. I might go over this with you next lecture. Okay, right now I want to concentrate on synthesis. And let's just see if we can practice this very quickly It says in 7.42, which of the following reactions is going to go at a faster rate? So you have a primary alkyl halide. Okay, you're treating it with a strong base, strong nucleophile. One of them you're in water, one of them you're in DMSO, and you get the same product. So what kind of mechanism is occurring here in this reaction? It's the same mechanism for both. It's just the rate is faster in one. Is this an SN1, SN2? SN1 or SN2? These reactions here, are these SN1 or SN2? You have a primary alkyl halide. It's SN2, good. So these are SN2 reactions. So which SN2 is going to go faster? The one in water, which is polar and protic, or DMSO, which is polar and aprotic? Yes, exactly. So the answer is DMSO, and it's because it is a polar aprotic solvent. All right, the next one, it's in the similar vein. We have a primary alkyl halide. They're both run in ethanol. We have sodium iodide and sodium chloride. All right. So it says which one of these is going to go to fast rate? Which would be a better nucleophile, iodide or chloride? Iodide is going to be a better nucleophile, right? So we'll put here, better nucleophile since more polarizable. All right, there we go. So that answers that. And I think it's the same question over here. And that ends the chapter. So that's the entire chapter.